I mean, first, there's not going to be any expansion, or I mean, maybe very slight expansion at the last talk, but yeah, I'm really an outsider, and I think the reason I'm here is Irit wants to learn about cubical complexes because she has all sorts of ideas of how to build expanders using cubical complexes. I don't know anything about expanders, and I'm not an expert on, I mean, things at all. But I'll tell you about cubical complexes. It's one thing I kind of understand. So what's the goal? The goal is to show you a family of complexes that sort of are, you can approach them in many different ways and somehow come up in nature for, at least for geometric group theorists, but hopefully also for other people, and we'll see some of those connections. And by now we understand quite a lot about the different ways one can consider cube complexes, but I'll start with really metric spaces, okay? So it's going to be quite general at first, and then we'll dive into cubical. So yeah, so you have a metric space, and we'll say this metric space is geodesic if you can connect any 2 points with a geodesic. So what does that mean? It means that for any 2 points in your space, there exists a map from an interval to your space, which is an isometric embedding. Means it sends points at the same distance to points at the same distance. Okay, so any 2 points can be connected by a geodesic. This doesn't have to be unique at first, but this is what it means for the space to be geodesic. Okay, now the main sort of notion here is the notion of non-positive curvature, or it's known cat zero. So this was something that coined by Gromov, but was studied before. It's an acronym. Has nothing to do with cats. Okay, so yeah, so what does it mean to be cat zero? So if for any 3 points, x, y, z, and for any geodesic triangle between those points, so what's a geodesic triangle? Just connect x, y with a geodesic, y, z with a geodesic, and x, z with a geodesic. Okay, so let me just write something like that. Okay, and for any 2 points, P and Q on this triangle. Okay, so here's the picture in the space X is the one on the left. I have a geodesic triangle and I have 2 points. And what we can do is, it's a metric space, so the distances between x, y, y, z, and x, z satisfy the triangle inequality. Okay, and any triple of numbers that satisfy the triangle inequality actually corresponds to a triangle in Euclidean space. Okay, so let's consider this triangle. So that's the one on the right. So for me, Euclidean space would be E2. Okay, and since P and Q sit on some geodesics, I can take the corresponding points in Euclidean, meaning the points with the same distances as P is to x, P hat should be to x hat. And now the condition is that the distance I measure in x is at most the one I'll measure in Euclidean space. Okay, so the slogan sort of is that triangles in our space are thinner or
pinched.
Sorry?
They're pinched.
Pinched, okay. But note that this is only a weak inequality, okay? So they're not wider than, maybe that's the right way, not wider than triangles in Euclidean space. Geodesic means that any 2 points I can connect with a path that sort of minimizes the length. Okay, let's put it in this language. But really it means, I can connect it with so there's a path from an interval to x so that, it connects x to y, satisfies that the distance between 2 points is the distance, the Euclidean distance. Yes, so they satisfy, so first of all, I choose x hat, y hat, and so on, so that they satisfy that they have the same distances as x, y, and z. Okay, so and the same for the p. So p hat, the distance from p hat to x hat, for instance, should be the same from. Okay, so along the same geodesic, I can sort of take the corresponding point. Let's see some examples and non-examples. So maybe the most trivial example is a Euclidean space itself. Of course, I mean, for example, the Euclidean plane. Obviously, it will satisfy this inequality. It will be an equality in this case. Another space is the hyperbolic space, if you're familiar with it. Trees. So this is where we connect more to the combinatorial size of things, which will be relevant later. So in trees, really triangles, geodesic triangles are sort of as thin as possible, right? They're really degenerate. Like the picture in a tree should look like this. Okay, so the distance between points will most likely be 0, or compared to the Euclidean. Okay, and products of spaces where you take in the product, you take sort of the L2 version of product. If the spaces were cat 0, then the product will remain cat 0. So now we can, form all sorts of things already with those things. Take products of trees. That's something people like to study. And maybe a non-example is take the sphere with its intrinsic metric. It is geodesic with its intrinsic metric, so the angle metric, but it's not cat 0 because triangles in the sphere tend to be fatter than the corresponding Euclidean. And maybe another example is sort of the corner of a cube, again with the intrinsic metric. This thing is in general, like for every triple of numbers that satisfy the triangle inequality, there exists a Euclidean triangle with the same distances, same edge lengths. So there exists. This is just like an exaggerated picture of that. So if you were happy with before. As promised, cat 0 gives us a lot of nice properties. So one nice property is unique geodesics. This is just running the definition, right? So I'm going to sketch a proof. This is x and y, and assume that there are two geodesics. Okay? Then I can treat this as sort of a degenerate triangle, x, y, y. Okay? And take the comparison triangle. The comparison triangle is a degenerate triangle in Euclidean space, and so distances should be 0, and so you have unique geodesics. This is compared to that. Okay, and maybe then the second thing is the space. If a space is cat 0, then it is contractible. Contractible means there is a continuous deformation of the space to a point. Okay, and one can imagine what this deformation would be. So just pick a base point in your space. Okay, this is my space. And then define this continuous deformation as take a point x and start moving it along a geodesic towards x0. Okay? And you might think this always works, but it doesn't always work. And the issue here is that cat 0 gives you continuity of this map. Okay? And this is why such spaces are contractible. And if they're contractible, I want to take one important property out of contractibility, which is simple connectivity. So we say a space is simply connected if for every closed loop in your space, okay, this is x, I can deform continuously this loop to a point. Okay. Any loop can be continuously deformed to a point, or maybe in another way of phrasing the same thing is that any map from a circle to your space can be completed continuously to a map from a disk to your space. Okay? Might use this if we get to the proofs later. Okay, and here's another definition. Oops, I'm missing this. Space is non-positively curved if it is locally cat zero. Okay, so what do I mean by that? Every point has a neighborhood, and in this neighborhood I see a cat zero space. Locally cat zero. Questions? Yeah, contractible means you can, so yeah, let me, can deform the whole space to a point. For me, this is the definition. Of course, when people talk about non-positively curved things, their intuition comes from Riemannian geometry. Okay, so you'll say that Riemannian manifold is non-positively curved if its sectional curvatures are all non-positive. And this is sort of the brilliance of Gromov is like taking this outside the Riemannian geometry setting and making it accessible to people like me that cannot understand Riemannian geometry. Okay, so yeah, so speaking of Gromov, there's this theorem, which is sort of his version of Cartan-Adamar theorem, that tells you that, in fact, this local property of being locally cat zero and this global property of being simply connected are enough to deduce cat zero. So if X is, so I should also assume complete as a metric space, locally cat zero and simply connected, then X is cat zero. Okay, but in a sense, this is sort of a recipe for us to build cat zero spaces, and then to achieve simple connectivity, one can pass to what's called the universal cover. Okay, so every nice enough space has a space that locally looks like the original space. Okay, so this is yeah, I don't know how much of a crash course on covering space theory I want to give, but every nice enough X, there exists a new space X tilde, which is called the universal cover. It will be also unique, such that, what do I want to say? Let me say P, yeah, what do I want to say? Let's say X tilde locally looks like X and simply connected.
Looks like in particular the metric is the same.
Right, so yeah, so the trick is always to sort of, I mean, this is a sort of a topological construction, and the trick is to pull the metric to X tilde so that locally it looks like X. So if X was locally cat zero, this X tilde will be locally cat zero, and actually the relation is even stronger than that. The X is the quotient of X tilde by some group. Okay, and this is where the group actions will come later. Okay, so maybe we are interested in finite objects. Okay, the X is this finite object. X tilde is usually an infinite object. Okay, and we'll see X as sort of a quotient of this infinite object by a group action. But this talk is only about geometry, so no groups yet. Okay, so now I don't want to talk about general cat zero spaces. I want to talk about cube complexes, cat zero cube complexes. So what's a cube complex? So I gave a very hand-wavy definition. It's a complex obtained by gluing cubes together. Okay, and the cubes could be from different dimensions. So let's just draw an example. And let me start by saying you all know cube complexes. You all know graphs, right? Graphs are glued up intervals. Okay, interval is such a cube. So that's my hand-wavy way of saying gluing together unit Euclidean cubes by isometries of faces, okay? So I'm not allowed to glue some weird stuff. Let me draw the example. I think it's better than writing a convoluted definition. So I can take, for instance, a square, glue an edge to it, glue a 3 cube to it. I think that's probably the ugliest 3 cube I've ever drawn. Okay, okay, so maybe something like that. It doesn't have to be simple. It could have loops.
Is it closed under taking faces?
Yes, you can consider the collection of all cubes to be closed up. Okay, now given such a thing, I can talk about the link of the complex at the vertex, and what I'll mean by that is sort of the combinatorial structure around this vertex, which one can imagine as sort of intersecting a very small sphere with the complex, or considering a small sphere in the complex around V. So let's do an example. So for instance, if this is my vertex V, okay, maybe I can do this trick, and consider the link. So I'll draw a small sphere around this vertex. So it would look something like that. Okay, right. So the link is naturally a complex of simplices, right? Because at each cube, I see sort of the corner in a cube, which is a simplex. Yeah, then the edges in the link are the squares in the complex around V.
Can you name?
Yes. Moshe? No. E. Okay, so this square S, say, will correspond to this edge S, okay? And here I have the cube C would correspond to this. Yeah? Good.
Would you be able to tell from the link if it's a loop or a couple of edges?
No, right? You cannot. I mean, so let's maybe do that. It's a good question. So let's consider this vertex now. Let's call it W. The link of this guy would be this smiley face, or not so smiley. Right. I mean, I see two vertices corresponding to sort of two edges that the vertex sees, but it doesn't know that it's the same edge. Excellent question. So again, comes Gromov and tells us exactly when a cube complex is non-positively curved. So when it satisfies this local condition, local cat zero. So it is locally, it is non-positively curved if and only if all links are simplicial. So simplicial complexes and flag. So flag simplicial complexes. Okay, so probably I should say what flag is. So flag means that whenever you see a click, there is a simplex feeding this click. Okay, it's the one skeleton of it. Every click is the one skeleton of a simplex. And if we go back to the example of something that was not cat zero, which was the corner of a cube without a cube, then this should demonstrate why this flag condition is important. So let me draw this example again. So I have three squares around the vertex. Okay. So imagine three squares around the vertex. That's the perfectly fine cube complex, but it's not going to be non-positively curved, as we saw. And now let's see it using this condition of Gromov. If I look at the link, which I think was green, the link is a triangle, but without the triangle inside. Okay, so it's not flag. I see a click, but I don't see a simplex filling this click. Okay, to make it locally cat zero at this vertex, I'll need to add the cube, the whole cube. Okay, and once I add the whole cube, then it's like filling this thing up.
So that geodesics become shorter.
Right, exactly. Yeah, so initially what I do, maybe I should have said it before. What do I mean by metric on this thing? Okay, so the metric, and we see actually two metrics on cube complexes, but the metric I'm referring to now is that you take...
You're an ant walking along the...
Sorry?
You're an ant walking along...
Exactly, you're an ant walking in this complex, okay, experiencing the Euclidean metric on each one of the cubes. Okay? So gluing up the cubes and sort of thinking locally as if you were Euclidean. Yes, and as Irit said, if you don't include the cube, the ends have to sort of go around. If you include it, the distances become shorter and short enough to be non-positively.
So when you say one skeleton, you don't mean the one cells, so right? Because when you had just
the one cells of the link, the one cells of the link are sort of two cells of your original complex, right?
you've said that. Oh.
Yeah, all links are flag simplicial complexes. Right, so I mean, every click I see in the link must be filled with a simplex. Yeah? No. No, don't do this. Let's work it out. So again, I'll empty this cube. The link at V is this graph. Right? I take a vertex for each edge. I take an edge in the link for each square.
So what is a click in?
So a click, well, we all know what a click is, but it's a graph now, right?
Okay.
So I take a click in the one skeleton of this. I mean, it's going to be a complex. So a click in the graph, and this is not flag, right? Because I see a click and it's not filled with a simplex. Every click is the one skeleton of a simplex. I mean, initially it's a simplex complex. I don't even know it's simplicial. And one of the requirements here is that it is simplicial. So what this is supposed to prevent is something like you take a square and, you glue two squares along two edges. This will give you something that in the link would look like a bigone, and this is not simplicial. So this is bad for us. So simplicial means what Gil referred to earlier, which is the intersection of simplices is a face, is one face. No, because I mean this. I'm limited to my, two-dimensional drawing and three-dimensional thinking. But I mean, you can imagine a four-dimensional cube that's missing, and you're only taking the three cubes around it. That's bad. This will give you a. This will give you a. Yes, exactly. I mean, the example we gave is just like triangles, so you see two-dimensional things. But if the click was an n click, then you'll see an n-1 simplex. Okay, great. So examples. The examples of you take the Euclidean space and you tile it by cubes, right? That's something that will satisfy this. And you can also do it locally, so you can consider, let's do one example of this. For instance, a torus divided in such a way. Okay, or yeah, it's the same as gluing this square. Trees that we saw before. And products, again, if you take a product of non-positively curved cube complexes, you'll get a non-positively curved cube complex. And maybe a slightly more advanced example is you take this surface, the bagel with two holes, but this is just the outside. Okay, and you can obtain the same surface by cutting along the blue. You get this octagon. okay? And cutting or chopping this up to squares, you'll get a non-positively curved cube complex. So you have to chop it in a certain way to get it. I mean, you can check it. Let's see that we understand the definitions, okay? And check that this is a non-positively curved cube complex. So here I'm including all of those vertices in red and also the vertices and edges in blue. Yeah, so what's the link, for instance, of this vertex? So this I can see easily that it's an 8 cycle, okay, which is flag simplicial. Okay, and the link, what about the red guy? And around them, so what do I see around this red guy? So I see an edge, which is the same as this edge, right? Another edge, something like that. So the link would actually look like a square in this case. Okay, and the blue guy I leave you to compute. Check that it works. Another important example is what's called the Salvetti complex. So this is a general construction that Danny will use in his talk. So you take a graph. Here's a difference. You usually denote your graphs with G, because you use G for the most important object, right? For me, obviously, groups are way more important than graphs, so saving this letter. No comment. Okay, so yeah, so how do you build a Salvetti complex? So you take a graph. Maybe let's do an example of a graph. Here's a graph. Keep it simple. Okay, and now you build the following complex. You take one vertex. Okay, you take a loop for each vertex in your graph. Okay, so loop or an edge, let's say. An edge for each vertex of V and V gamma.
Want to write a Moshe beside one vertex so we know which.
Yes. Okay. And now you want to introduce higher dimensional cells corresponding to cliques in gamma. Okay, so for every clique in gamma, I'll glue in a torus, so a product of S1s. Okay, so I kept it two-dimensional so that I can draw something, but so for the clique, the only clique that I have here, which is BC, I take a torus on a two torus, sorry. Okay, so this is my two torus. And I glue it to B and C. Yeah, so B and C back to this guy. Okay?
Is this a cubical complex?
It's a cubical complex, right? Cut this thing along the green, and you'll get a square, right? So really what I did is I took a square. You can think of it as taking a square and gluing this to the edge C, oriented in such a way, and this to the edge B. Okay, this is a two-dimensional example, and higher dimensions, you take higher cubes and you glue them to what you have added previously. And this turns out to be non-positively curved. I'm not going to check the link with you, but it's somehow related to that.
To what?
To the graph gamma. To gamma. Yeah. Okay, and maybe let me add that this also corresponds to a group called the right-angled Artin group gamma, which is the group generated by the vertices of V gamma. Okay, so I'm going to write a group presentation. If you know it, good. If you don't, this talk is not about groups. Okay, so you add the relation V commutes with U for every edge. Okay, and the relation is to something called fundamental group. So the fundamental group of this complex is going to be this outing group. Okay, maybe I'll skip Davis complexes and maybe get back to them in my third talk.
Nir, can I ask you about the Salvetti complex? So is it the same as saying, let's go over the list of all inextendable cliques? For each one, we create just a cube of the corresponding dimension, and then we identify along common sub-cliques. Is that the same?
Yes.
Okay, thank you.
But note that the initial thing is loops, yeah? So yeah. Yeah, so maybe in a sense you're including the empty clique. This is the vertex that you start with. You start gluing things to that. Okay, yeah, so why cat-zero cube complexes? So the reason is that they come with this extra structure that's captured by something called hyperplanes and half spaces. Okay, so for this we need another definition. So a mid-cube is the following subset of the Euclidean cube. So it's 0, 1 to the n minus 1 times 1/2. Okay, so something that looks like that. And now let's consider the complex that you get by considering all mid-cubes of your given cube complex. Okay? And gluing them along the mid-cubes of faces. Again, hand-wavy sentence. Let's do an example. Before you ask questions, let's do an example. Okay, so I've taken this cube complex, okay? And what do I want to do? I want to consider all possible mid-cubes, okay? And glue them together whenever they match. Okay, so for instance, this is a mid-cube, right? Okay, and note that also this sort of vertex is a mid-cube. It's a mid-edge, right? And same for this guy. Okay, so that's going to be sitting somewhere here in my space that I'm building. Okay, and but I'm not done. I have more mid-cubes to consider. So let's obviously I have this guy and so on. I'm not going to do all of them, but let's do the interesting one. The interesting one is this guy. Okay, so I start with this mid-cube.
This 3 cube is full?
Is full, yeah, is full. Okay, so here, this is attached to this mid-cube of the 3 cube. Yeah? So let's draw it on the side. So on the side, it would look something like that. And now I continue. This is attached to that, so on, and so on, so on, so on.
Oh, so you get half also on the right? So it's not just everything and then a half. It's a half and...
Yeah, I didn't tell you how to... Yeah. So I should count maybe, whatever. And here another mid-cube, right? Okay, so this is part of the space I'm now creating.
Somehow you don't see the intersection.
I don't see the intersection. Yeah, I don't put it in as part of this data. But of course, this blob of things comes with a map back to my complex.
For this solid cube, you even have another one.
There is another one, yes. Good. All paying attention, right? There's this guy, which sits here in this. Okay, and a connected component of this thing I'll call a hyperplane. Okay, so this huge red thing is a hyperplane, the blue thing is a hyperplane. Maybe I should note that hyperplanes could just be points, right? If this is an edge, then this thing is a mid-cube and corresponds to hyperplane. Is a connected component of this cube complex. Okay, so that's you're one slide ahead. Good. So if X, so far I just defined it for a cube complex, but really it's interesting when the cube complex is non-positively curved, and when X is non-positively curved, then this map from a hyperplane to X is a local isometry. Okay, and has an image that's locally convex. Let me put it there. And putting those things together, you get that it is NPC itself. Okay, so the hyperplane and H is NPC. Okay, so each hyperplane itself is non-positively curved, and this is not a difficult thing. I mean, right? Locally, we know how the map looks like. It looks like take H and put it in H times an interval. Right? I mean, if you look at a point here of H, then H sort of sits in something that looks like H times an interval locally. Okay. But now actually, if X is cat 0, then we can upgrade being just a local isometry and being non-positively curved to actually being an embedding. So then H sort of embeds in X. Okay, has a neighborhood that looks like H times 0, 1. Okay, so it's not only locally, it's globally, it looks like H times 0, 1. And when I remove H from X, I get two components. Oops. Okay, and that's really the reason why we care about it so much. Okay, so this two components, we'll give them names. They're going to be called the half spaces. A half space is a component of X minus H for some hyperplane H. Okay. And of course, I'm assuming here X is cat 0 for this. Yeah.
What is X minus H?
Just remove H from the space. Yeah.
Just to make sure that I'm with you, they don't need to be identical or isomorphic, the two halves.
I didn't follow. What doesn't need to be identical?
They need not be isomorphic, the two half spaces.
Side of the hyperplane.
Yeah, so maybe the example we all know is that of trees. I mean, we use this fact all the time when we deal with trees, and the whole idea is sort of generalize this to higher dimensions. So yeah, a tree is a perfectly good example of a cat 0 cube complex. Okay, what are the hyperplanes in this case? The hyperplanes are just mid-edges, right? So this, for instance, is a hyperplane. Okay, and maybe following the question before, let's make the two half spaces not the same, right? When I chop along this red, I get two components. A neighborhood of the red looks like a product of the point times an interval. Yes, I didn't say that.
What do you mean?
So each mid-cube is obviously a cube, right, on its own, and so you get a cube complex. The way you glue them is sort of also along faces. So it is a cube complex, and the point is that it stays non-positively curved if X was. I mean, this was sort of,
Function.
you see here this doesn't embed, right?
Yeah.
This red thing cuts itself. So I want it to be, so if X was cat 0, obviously this is not cat 0.
Yeah, we saw it's not simply connected, right? So.
Right, so I see. Yeah, you can delete the edge if you want, and consider if you want it to be subcomplexes. You can. That's a matter of convention, and but what do you? There's really the expert, and whatever he says is sort of.
I'm saying edges.
So
It's up to you. For me, let's say
if it's open or closed.
the most important thing is like which vertices are on this side and on this side or the other.
You don't
Let's
think of
say
the
this
half
is.
space. You don't think of the half space as a cubical complex. You think of the half space as a submetric space of the original space. Right?
You can also delete the edge or the neighborhood of H and really think of it as a sub-complex.
Yeah.
That's perfectly fine. Okay, so if you want maybe this or X minus this neighborhood, yeah, half neighborhood of H, up to you. It's not going to matter much. So here's why we want those things is that actually the hyperplanes gives us metric information about X that was sort of hidden in the combinatorics of the cube complex. So first, let's define a new metric on the cube complex. This is going to be, some people call it the L1 metric or the combinatorial metric. And this is just the metric on the vertices that comes from shortest path. Okay, so shortest path in the one skeleton. Okay, so the metric you're all used to, right? Doing expansion. Great. Note that this is different from the previous metric that we had, which is the Euclidean, the one coming from the Euclidean or the L2 metric. For instance, on a square, this is square root 2, but now I'm measuring it as length 2, right? 1 and 1. And I'm losing some things when I do that. So for instance, I can still talk about geodesics, and now they're not going to be unique. Even the square example gives you an example of something like that. But here's a nice lemma that's extremely useful, is that this distance of shortest path between vertices is actually something you can measure in terms of the hyperplanes. Okay? So how do you do that? So the distance between u and v is really the number of hyperplanes h. Maybe I assume I need some assumptions, right? X is ket 0, a ket 0 cube complex. Yeah. Then the distance between u and v is exactly the number of hyperplanes that separate u and v. So h separates u and v. Okay, and I will not be able to prove it, but let's just maybe try 1.5 minutes. So there's one inequality that's easy. The inequality that you at least have to cross all the hyperplanes that separate u and v when you go from u to v, right? So this inequality. So this is obvious, very easy. Do we all see that? It's usually the difficult inequality when you measuring distances, right? But here it's easy. You have to cross all hyperplanes that separate u and v. Okay, what about the other one? So the other one really tells you that any shortest path between u and v crosses each hyperplane once, right? So let's imagine that this is not the case. So this inequality. So imagine that I go from u to v, and at some point I cross the hyperplane, and then I crossed it again. Okay, so this is my hyperplane h. I crossed it twice. I crossed it many times. But now let's look at the sort of shortest possible interval where this happens. Okay, where I cross some hyperplane twice. Okay, so I want sort of this to be shortest possible. Okay. Oh, now it's even yelling at me that my time is up. I'm going to do it very quickly. Every edge here crosses some hyperplane, right? Because there is a mid cube along a mid edge along this thing. And from my assumption about the minimality of this interval, I know that this hyperplane must cross h. Sorry, must cross h, but must not must separate u and v. Oh, that's not true. Sorry. Doesn't go back here. This is all I need. Doesn't go back here. Okay, so in fact from this, just from looking at those edges, you get that the red and green must intersect, and if they intersect, the exercise below tells you actually there's a square in my complex there. Okay, and now I can change my path. Instead of going along the blue as before, like this, I'll change it to go through here. What did I gain? I gained that my interval, my blue interval from the beginning got shorter. Okay, so by induction at some point it's going to be 1 point, and 1 point just means you're backtracking. Okay, so that's kind of a...
Why is the exercise?
Yeah, so here, I mean, when I thought about this, I was planning on like using cat zero geometry. There's like a triangle you can draw, Euclidean space that would still tell you that they must intersect.
Yeah, you should use somewhere on the fact that it's cat zero.
Right. So it's hidden there. Okay, so thanks.